Axiom 1. Axiom 1 states that if let A and B are two non-empty sets, are two non-empty sets. If there doesn't exist a surjection or onto function from A to B, we say B has more potential than A. If there doesn't exist a surjection, that is onto function, if there doesn't exist a surjection or onto function from set A to B, we say B has more potential. We say B has more potential than A. That is, potential of A or the cardinality of A is less than the cardinality of B. For instance, if I define a set A as A, B, C and B as X, Y, W and Z. Let's define a function from A to B. In such a way that A is mapped to X, B is mapped to Y, C is mapped to W. Here, all the elements of A is mapped to distinct images in B. Here, all the elements of A are mapped to distinct images in B. That is, A is mapped to X, B is mapped to Y and C is mapped to W. None of them share common images. That is, A and B doesn't have common images, doesn't share common images. None of the two elements in A share common images. Therefore, we say this function is 1, 1. Therefore, f is 1, 1 since all the elements in A have distinct images. And since one of the elements in B is left out, is left unmapped, we say this function is not onto. F is not onto as well. Sorry, it's not onto. Why is not onto? Because there is an element in B, Z, that doesn't have pre-images. Since there exists an element Z in B that doesn't have pre-image. This element Z doesn't have pre-image in A. Therefore, this function is 1, 1 but not onto. Hence, we can say that the cardinality of A is less than the cardinality of B. Here there is no possibility of onto function between the set A and B. Therefore, this function is 1, 1 but not onto. Hence, the potential of the set A is less than the potential of set B. That is, the cardinality of set A is less than cardinality of set B. This is axiom 1. Axiom 2. Axiom 2 states that if A and B are two sets, if A and B are two non-empty sets, and if there doesn't exist a 1-1 function from set A to set B, from set A to set B. 1-1 function means injective function. If there doesn't exist a 1-1 function from set A to set B, we say A has more potential than the set B. That is, the cardinality of A is greater than the cardinality of B. Small example, if I define a set A as A, B, C and D, and set B as X, Y and Z, and define a function f in such a way that A is mapped to X, B is mapped to Y, C is mapped to Z, and D is mapped to Y. So here we see that C and B, the element C and B, B and D, B and D, the element B and D of the set A shares a common image, that is Y. Therefore, this function is not 1-1. Hence, we can say that the potential of A is greater than the potential of B. That is, the cardinality of set A is greater than the cardinality of set B. This is axiom 2. So let me repeat axiom 2 once again. A and B are two non-empty sets. If there doesn't exist a 1-1 function from set A to set B, we say that potential of set A is greater than the potential of set B. That is, the cardinality of set A is greater than the cardinality of set B. The final axiom, that is axiom 3. If A and B are two non-empty sets, if there exists a 1-1 and onto function, that is a bijection between the set A and B, we say that if there exists a bijection, that is 1-1 onto function between the set A and B, and these two set A and B are non-empty sets, then we can say that the potential of set A is equal to the potential of set B. That is, the cardinality of set A is equal to the cardinality of set B. And an example, if I define a set A as A, B, C and D, and set B as W, X, Y and Z, and define a function from A to B in such a way that A is mapped to W, B is mapped to Y, C is mapped to X, and D is mapped to Z. That is, image of A is W, image of B is Y, image of C is X, and image of D is Z. So here we notice that all the elements, every elements of A has distinct image in B. Therefore this function is 1 1, and every element of B has pre-image in A. Therefore this function is onto as well. Therefore this function f is 1 1 because every element has distinct image in B, as well as onto because every element in B has pre-image in A, and onto. Hence we say that potential of A is equal to potential of B, here is equal to potential of B, that is the coordinate of A is equal to coordinate of B, that is 1 2 3 4, that is 4. This is axiom 3, that states that if A and B are two non-empty sets and if there exists a 1 1 onto function between them, we can say that potential of A is equal to potential of B, that is coordinate of set A is equal to example. Let's discuss a concept through an example. Let me define a set A as A, B, C, D and E, and I define a function f from A to its power set in such a way that, okay, let me draw the Venn diagram. A as A, B, C, D and E, and second set B as, second set B is the power set. It's a B set, that's the power set of A. Defined as singleton set A, set AB, set BC, set ACD, and set AD, empty set, set BD, etc. This set B, that is a power set of A, contains all the subset of A, and this is set A, and we are going to define a function from set A to its power set. Let me define a function from set A to set B in such a way that A is mapped to singleton set A, B is mapped to AB, C is mapped to AD, C is mapped to AD, D is mapped to BC, and E is mapped to ACD. That is, image of A is singleton set A, image of B is equal to singleton set, is equal to set AB, image of C is equal to set AD, image of D is equal to set BC, and image of E is equal to set A, C and D. Here we see that this element f of D, f of E and f of C, f of C, f of D and f of E. In this set we see that the element C doesn't belongs to this set, that is that doesn't belong to the image. image of C is mapped to set AD, but C doesn't belongs to their image, that is AD. Image of D is mapped to B.Sc, but D doesn't belongs to their image, that is B and C. And image of E is mapped to set ACD, but E doesn't belongs to the image ACT. So from here we can construct a set. From here we can construct a set X as set of all elements in A, such that X doesn't belong to that image, that is f of X. Here X is, since C, D and E doesn't belongs to their image, therefore we collect C, D and E in the set X. X is collection of all the elements in A, such that those element doesn't belong to their image, that is C, D and E. These three elements doesn't belong to the image. So X is a set that we have constructed from this fact. So we have defined a set X as set of all elements in A such that X doesn't belongs to that image. And image is the elements of the power set of A. So this implies X is C, D and E, and this X is also a subset of A, and we can name or we can call this set as set of all bad elements. Why? Just for the sake of understanding, we call this set X as the set of all bad elements, because these elements C, D, E, they doesn't belong to that image. Here a note to be taken that X in general, X can be empty set. Now our claim is for every function. Now we can claim that for every function from A to its power set, we can construct a subset A, which is a set of bad elements by every function. We can claim that for every, let me write down, for every function we defined from set A to its power set, we can construct a subset X of the set A, which is a set of bad elements, That is, whenever you give me a function from set A to its power set, I can give you a subset of A which is a set of bad elements. That is, whenever you give me a function whenever you give me any function from set A to set B, from set A to its power set, then I can assure you with a subset of A, which is a set of bad elements. Then I can give you a subset X of set A, which is a set of bad elements, This subset X can be set A, can be non-empty set, or can be any subset of A. That is, can be any elements of its power set of A. Now the next topic is Cantor's theorem. Cantor's theorem. Cantor's theorem states that from any non-empty sets to its power set, there cannot be an onto function defined. Let me write, from any non-empty set A to its power set, that is P of A, we cannot define an onto function. So what does Cantor's theorem state? From any non-empty set A to its power set, we cannot define an onto function. That is, if A is a non-empty set, and if I define a function f, if I define an arbitrary function f from set A to its power set A, then this function f cannot be an onto function. And that is, the cardinality of set A is less than the cardinality of its power set A. That is, cardinality of set A is less than 2 to the power the cardinality of A. So now let's prove this theorem in the next page. Let's start the proof. Let's define a function f from set A to its power set. If x is an element of A, we can say that its image is the element of its power set. This also implies f of x is a subset of the set A. Why? Because f of x is the elements of its power set P of A, and P of A is a collection of all the subset of A. Since P of A is a collection of all the subset of A, we can say that f of x is a subset of A. Now let's define a set X, that's a collection of bad elements, as set of all elements of A such that X doesn't belongs to its image. and this set is called the collection of bad elements that we have discussed earlier, that a set, the collection of bad elements if all the elements of A, such that X doesn't belongs to its image. This further implies that this set X is also a subset of A. That is, X is an element of the power set of A. This X can be the non-empty as well. Can be non-empty, can be the set A itself, or can be any element of the power set of A. Now, if f is onto, if f is an onto function, that's an assumption, then there exist an alpha elements of A such that f of alpha is equal to X. What is X? X is a collection of bad elements. That is, X is equal to set of all elements of A such that X doesn't belongs to its image, that is f of X. So now we have alpha elements of A and X as a subset of A. From here two cases arises. That is, if alpha is an element of X, then this implies alpha doesn't belongs to its image, because X is a set that contains all the elements that doesn't belongs to their image, and since alpha is the element of X, we say alpha doesn't belong to its image. That is alpha doesn't belongs to X, because you have taken in an assumption that f of alpha is equal to X. Since f of alpha is equal to X in our assumption, so hence contradiction arises, because in our assumption we have taken alpha belongs to X and we got a conclusion that alpha doesn't belongs to X. Hence there is a contradiction. Now this is case 1. In case 2, if alpha not the element of X, this implies alpha belongs to f of alpha, then this further implies alpha belongs to X, because f of alpha is equal to X. Since f of alpha is equal to X in our assumption, hence a contradiction. So in either of these cases we are coming up with contradiction. Therefore we can say that no such alpha exists. Why? Because since there is an ambiguity of inclusion or exclusion. Inclusion of object. we say further, finally we say that no such element alpha exists. This further implies f cannot be onto, that is cardinality of A is less than its power set, less than the cardinality of power set, by axiom 1. Why? Because axiom 1 states that if f cannot be onto between the set A and the power set A, we say that the cardinality of the first set A is less than the second set B. Hence the proof. Note, from Cantor's theorem we can say that potential of a natural number is less than the potential of its power set n. That is, though both the sets are infinite or transfinite, that is, the cardinality is transfinite or transfinite, though both the sets are infinite or transfinite, there may be a potential difference between the infinite set, between the infinite sets. Example, cardinality of natural set is less than the cardinality of its power set. These two sets are infinite set, but the cardinality are different. The cardinality of n is Aleph null and the cardinality of power set is continuum. From here we can say that Aleph null is less than continuum. This Cantor's hypothesis, or it's also called as continuum hypothesis. Continuum hypothesis. This hypothesis states that there is no transfinite number between Aleph null and continuum. Why it is called hypothesis? Because this statement, this proposition is not proven but taken as a fact without proof. Therefore, it's called hypothesis. What this hypothesis states that? This hypothesis states that there is no transfinite number between Aleph null and continuum. That is, there doesn't exist a set which has more potential than that of natural number but has less potential than of its power set. Let me write down. That is, there doesn't exist a set which has more potential than that of natural number, but has less potential than that of the power set of natural number than that of the power set of natural number. When two infinite sets are similar, the same transfer number is used to denote the cardinality. Okay, first what you have stated, there is no transfinite number between Aleph null and continuum. That is, there doesn't exist a set which has more potential than that of natural number but has less potential than of power set. That is, between Aleph null and continuum, between these two numbers there doesn't exist any transfinite number. That is, C is the successor of Aleph null. What more we can say that when two infinite sets, this also implies that when two infinite sets are similar, then the same transfinite number is used to denote the cardinality, to denote their cardinality. That is, if set A is similar to the natural number, then we can say, and set A is an infinite set and natural number is also infinite set. If an infinite set A is similar to a natural number, we can say that the coordinate of A is equal to coordinate of n, that is equal to Aleph null. Let's define a function. This is an example. Let's define a function from natural number n to an integer z. N is, where n is a natural number 1, 2, 3, 4 ... and z is set of all positive and non-negative numbers, that is -3, -2, -1, 0, 1, 2, 3. Okay, let's define a function from n to z such that f of n, n is the element of natural number. F of n is equal to negative of n minus 1 upon 2 whenever n is odd, and n upon 2 whenever n is even. Here we see that let me draw the table. And f of n. If n is 1, f of n is 0. If n is 2, image of 2 is 1. If n is 3, then its image is -1. If n is 4, then its image is 2. If n is 5, then image is -2. If n is 6, then its image is 3. If n is 7, then its image is -3, and so on. Here we see that, what we can see that every elements from n, every element from n has distinct image. Every element of n, that's a natural number, has distinct image. That is, 1 has image 0, 2 has 1, 3 has -1, 4 has 2, 5 has image -2. All the elements of n has distinct image. Therefore, we can say that f is 1 1 as 1 1. And we also see that fn covers all the elements of z. Here fn covers all the elements of z. 0, 1, -1, 2, -2, 3, -3, and so on. Since fn covers all the elements of z, that is, all elements in z have pre-images in the set n. Therefore, we can say that f is 1 1 as well as onto. Why onto? Because fn covers all the, that is range, that is fn. This is a range that covers all the elements of z. Since fn is equal to z, that is fn cover all the elements of z, that is all the elements of z has pre-image in the set n. We can say that this function is onto as well. Therefore, f is 1 1 and onto as well. Therefore, we can say that n is similar to z. Thus, this implies cardinality of z is equal to cardinality of n, that is equal to Aleph null. Thus, we say that the set z is countable. A point to be noted here is that a note, let's take it as a note, an infinite set is similar to its proper subset, An infinite set can be similar, an infinite set can be similar to its proper subset. Let's take an example. If I define a set, if I define a set from natural number, a subset, that n is a natural number, and if I define a subset A of a natural number as A is a subset of natural number, and define A as 2, 4, 8, 16, 32. This is a subset of natural number. Let's define a function f from n to a such a way that f of n is equal to 2 to the power n. This function is 1 1 and onto as well. This function is 1 1 and onto. Why? Because for every n in natural number we will get an image. Will get an image in A, and for every image and for every elements in A we have a pre-image in set n. Therefore, this function is 1 1 onto, and hence we can say that the cardinality of A is equal to the cardinality of n, that is equal to Aleph null. Here this infinite set A and is a subset of natural number, but the cardinality of set A and n is same, that is Aleph null. Now let's take the definition of counting. Definition: we can say elements of a set can be put under counting system or counting process if there is a rule by which first or initial member can be defined and the successor of every member can be defined till the set last. Okay, let me write what I said. If we can define, if we can say elements of a set A can be put under counting system or counting process if there exists a rule by which first or initial member of a set can be defined, by which first or initial member of a set A can be defined, as well as successor of every member can be defined. Successor of every member can be defined till the set lasts. Let me repeat it again. We can say elements of a set A can be put under counting system, a counting process, if there exists a rule by which first or initial member there exists a rule by which first or initial member of a set can be defined, as well as successor of every member can be defined till the set last. So let's take an example. If I define a set A as A, B, C, D and E, let me define a rule by which I can count all the elements of A. Let me label A as 1, C as 2, B as 3, D as 4, E as 5. So what's the rule? F of A is 1, F of B is 2, F of C is 3, F of D is 4 and F of E is 5. So this is a rule by which we can count the elements of A. A is the first element, that is A is the first element of A, and F of B is 3 here and F of C is 2. A is the first element because we label A as 1, and C is the second element because we label C as 2, and B is the third element, D is the fourth element, and E is the fifth element. This is how we label the elements of A, and thus we can count the elements of A as well, as 1 first element 1, second element 2, third elements B, fourth element D, and fifth element E. And at the last element the set exhausts, or the set ends. Here the counting ends at the fifth elements. Here counting of all elements in A ends or last at fifth element, that is E. Since E is the fifth element, we can say the coordinate of A is 5, because our counting process ends at the fifth element, 1, 2, 3, 4 and 5th. What is countable set? Now let's define what is countable set. Countable set. A set is countable. A set is countable if all the elements of the set, X, let's see, a set X is countable if all the elements of the set X can be put under counting system or counting process. If all the elements of X can be put under counting system, then we can say that the set X is countable or countable set. This countable set can either be finite or countably infinite. This countable set is either finite or countably infinite In other words, I can say that if I define a 1, 1 onto function from Sn to set A, if I define a 1, 1 onto function, that is 1, 1 and onto, we can say that A is finite, and here A is also countable. Is finite or countable. Or if I define a function from natural number to A, that is 1, 1 and onto, we can say that this A is infinite and countable. That is, A is called countably infinite. Why? Because it is infinite as well as countable. Therefore, this set A is called countably infinite. When it is called countably infinite? If I can define a function from natural number n to the set A, that function is 1, 1 and onto as well, then we can say that f is infinite as well as countable. Hence, A is called countably infinite. And if I define a function from Sn, that is initial segment of natural number Sn, to the set A by the function f, that is 1, 1 onto, then we say that the set A is finite or countable. Calling finite is enough to conclude that the set is countable. Therefore, there is no need to mention countable for a finite set. Now let's take some notes. Note 1. If A is finite, then we say P of A is finite. But cardinality of A is less than the cardinality of power set of A. Second, if A is infinite, then P of A is also infinite. Here, if A is infinite, here if, for example, if the cardinal of A is Aleph null, then cardinality of P of A is continuum. That is, cardinality of A is less than the cardinality of this power set. So note 1 is, first point is, if A is finite, then P of A is finite. If A is infinite, then P of A is also infinite. But third, but A will never be similar to P of A. A will never be similar to P of A. Why? We have discussed in Cantor's theorem. According to Cantor's theorem, we can say that A will never be similar to P of A. That is, there doesn't exist an onto function from A to its power set. So therefore we can say that A will never be similar to its power set. And here A can be finite or infinite. Okay, write the reason why A will never be similar to P of A by Cantor's theorem. Fourth, if A even become countable infinite, countably infinite, then P of A can never be countably infinite. Why? Reason is Cantor's theorem. By Cantor's theorem and Cantor's hypothesis, that is continuum hypothesis, and by Cantor's hypothesis. If A become countably infinite, say the cardinality of A is Aleph null, that is countably infinite, then power set of A, the power set of A is always greater than the set itself. Why? By Cantor's theorem. And since by Cantor's hypothesis we say that there doesn't exist any transfinite number between Aleph null and C, we can say that the cardinality of A is less than the power set of A, and the cardinality of A is Aleph null, and the power set of A is continuum, and this is strictly greater than Aleph null. Therefore we say that even if A become countably infinite, P of A can never be countably infinite. It is always uncountable set. P of A is always, that is, P of A is always uncountable. Reason is, by Cantor's theorem, the cardinality of power set of A is greater than the cardinality of the set A, and by Cantor's hypothesis we say that there doesn't exist any transfinite number between the cardinality of A and the power set of A. Therefore we say that P of A is always uncountable, and its cardinal is always a continuum. C. Therefore, we say that a set X is said to be uncountable if it is not countable. If it is not countable, that is neither finite nor countably infinite. Neither finite nor countably infinite. Example: P of n n cross P of n. These all sets are neither finite nor similar to n. These all sets are neither finite nor similar to n. Why? By Cantor's theorem. By Cantor's theorem, we can say that these are neither finite nor similar to n. Now let's take one example. If I define a function, let's take one example. If I define a function f from power set of n to n cross P of n, and define f of x is equal to 1, x. First, let's check it is 1, 1 or let's check whether it is 1, 1 or not. First, f of x is equal to f of y. This implies 1 of x is equal to 1 of y. Then by the properties of order pair, we can say that x equal to y. Hence, we can say that f is 1, 1. And this implies that P of n, the cardinality of P of n is less than or is equal to the cardinality of n cross P of n. This further implies that this cardinality of P of n is strictly greater than Aleph null. Strictly greater than Aleph null. And this is less than equal to the cardinality of n cross P of n. Hence here we can say that P of n is uncountable because it is strictly greater than Aleph null, and Aleph null is the cardinality for countable infinite set. And since it is strictly greater than Aleph null, we can conclude that P of n is uncountable set. A note: every countably infinite set has cardinality Aleph null. Every countably infinite set has cardinality Aleph null, whereas two uncountable set may have different cardinality but always greater than Aleph null. Let me write down: every countably infinite set has cardinality Aleph null. whereas two uncountable sets may have different cardinality. Two uncountable sets may have different cardinality, but always greater than Aleph null. But always greater than Aleph null. Example, let's take an example. P of n, if cardinal to P of n, we know cardinal to P of n in C, that is continuum. Then P of n is 2 to the C. Why? By Cantor's theorem. Why? Since by Cantor's theorem. What does Cantor's theorem tell? It tells that there doesn't exist an onto function between a set and its power set. Therefore, the cardinality of the power set of A is always less than the cardinality of its power set. The cardinality of the set A is always less than the cardinality of its power set. Okay, that is cardinality of the set A is always strictly less than its cardinality of its power set. Since by Cantor's theorem we can say that power set of n is equal to 2 to the C. Why C? Because C is the cardinality of P of n. That is 2 to the power P of n is equal to 2 to the C. So here we can say that 2 to the C or C is less than 2 to the C. A note, let's take a note. Aleph null we can denote it as C naught, continuum naught, read as continuum naught, and C as continuum 1, that is continuum 1, and C2 as continuum 2, continuum 2, and so on. 2 to the C is generated 2 to the C. 2 to the C is continuum 2, that is denoted by C2, and C is denoted by C1, that is continuum 1, and Aleph null is also continuum, that is called continuum naught. This also we can take it as a special note. Let's recap what is axiom of choice. Axiom of choice. If you have collection of all sets, if X is a collection of all non-empty sets, if X is a collection of all non-empty set, then we can pick or choose at least one element from from each set, from each non-empty set, from each non-empty set of the collection X by a rule. By a rule, we can pick or choose at least one element from each non-empty set. From each non-empty set, that's the element of X. So X is a collection of all non-empty set, and from each non-empty sets, we can choose or pick at least one element using some rule. This is called the axiom of choice. Now let's discuss a lemma. Now let's discuss a lemma. This is lemma 1. Lemma 1 states that every infinite set has a countably infinite subset. Every infinite set has a countably infinite subset. Every infinite set means this can be countably infinite or uncountable set. So infinite set means an arbitrary infinite set, not necessarily countably infinite. It can be countable infinite or uncountable set. So what does lemma 1 state? Lemma 1 state that every infinite set has a countably infinite subset. Let's discuss the proof in the next page. Proof. Let X be an arbitrary infinite set. Let's take X as an arbitrary. Let's take be an arbitrary. Let's X an arbitrary infinite set, that is can be countable or uncountable. That is either countable or uncountable. Now let's pick or select. Now let's pick an element X from X. Now let's pick X from X using axiom of choice. By axiom of choice, we can pick an element X from X, because axiom of choice gives us a permission that from any set we can pick an element from that set. If X, okay, let me write down the axiom of choice. If P is a collection of all non-empty set X, capital X, then we can choose or pick an element from each non-empty set X. Then by some rule we can pick an element from each non-empty set X, from each non-empty set X of the collection B. So this is what axiom of choice state. So using this axiom of choice, we can pick an element we can pick an element from a non-empty set X. Therefore, using axiom of choice, we're gonna pick an element X from a non-empty set X, and this set X is an arbitrary infinite set. Arbitrary means it can either be countable or uncountable. So we pick an element X from capital X, and we name this X, and we name this X as A1. Now we define a set A1. Now let's define a set A1 as a singleton set A1. This A1 is a collection of collection of element A1. Just single set A1. And after define a set A1, again by axiom of choice, we pick an element X from X minus A1. That is, X cannot be A1, and we rename this new element X, that is the element of X minus A1, as A2. Now let's rename this new element X as A2. Now again define another set A2 as the collection of A1 and A2. Again by using axiom of choice, we picked another element X from X minus A2. That is, X is not A1 and X is not A2, and we rename this new element X, that is the element of X minus A2, as rename this new element X as A3. And again we defined a set A3 as A1, A2 and A3, and we keep doing this same process. And if we keep on doing this process, we finally defined a general set AN. We finally define a general arbitrary set AN as AN minus 1 union singleton set AN, that is set of A1, A2, A3 dot AN. Now we define A as, this set A is equal to union of R to 1, R is equal to 1 to infinity AR, that is equal to U union of AR, where R is element of natural number. That is, A is equal to A1, A2 dot AN plus 1 dot. So what we have defined A as, so let me write it again. We define A as union of R is equal to 1 to infinity AR, which is equal to union of AR, where R is the element of natural number. This further implies that A is A1, A2 up to AN. then again an plus 1, an plus 2, dot dot till infinity. From here we can say that every elements of A is labeled by the elements of natural number. That is, first element is labeled as 1, second elements is labeled as 2, and this nth elements an is labeled as n. This element is labeled as n plus 1, and this element is labeled as n plus 2. Since all the elements are labeled by the elements of natural number, we can say that this set A is countably infinite. That is, this set A is a subset of X as well, and this X can either be infinite or countable infinite or uncountable. This set S can be countably infinite or uncountable. This is arbitrary, that is, this is arbitrary infinite set. Therefore, since A is countably infinite, we can say that A is similar to natural number set. Hence proved. So what we can say that since X is an arbitrary infinite set, so we can say that for all infinite set X there exists a countable infinite set A, that is, A is similar to n. This is the final conclusion of the proof. Now from the last proof we can define a function f such that f is defined from n to the set X, and such that different function n to set X such that f of r is equal to a of r. Here this implies f is 1 1 but not on 2, but may not be on 2. Therefore this further implies that the coordinate of natural number is less than the coordinate of X. Here X can be here X is countably infinite or uncountable. So we have defined fr equal to ar, and this implies f is 1 1, may or may not be on 2, because we don't know whether this set X is a countable or uncountable set. Therefore this implies coordinate of n is less than or equal to the coordinate of set X. Thus from here we can say that Aleph null is less than or equal to the cardinality of the set X. Thus here we can say that Aleph null is the smallest transfinite number, and two notes. Let's take two notes or observation from lemma 2, or observation from lemma 1. First is among uncountable sets P of n is the smallest one. P of n is the smallest one. Second, this is by Cantor's hypothesis. By Cantor's hypothesis. By Cantor's hypothesis, we say that among all countable sets, P of n is the smallest countable sets. Uncountable set is the smallest uncountable set, P of n. Second, among countable sets, n is the smallest countable sets.